Hello everyone, welcome back. In this video, we will debug an ARM7 assembly program that assembles successfully but contains several runtime and logical errors. Let's begin. Let's examine the very first instruction, LDR R0, array 1. Now look at register R0. Notice that register R0 contains the value 20. At first glance, this may seem reasonable, but let's verify whether R0 is actually pointing to our array. Open the memory window and enter the value in R0 as the address. Notice that the values stored at the location are not 20, 30, 40 or 50, which are the four elements of array 1. This tells us that R0 is not pointing to the array. The instruction LDR R0, array 1 has loaded the first value stored at array 1, which is 20, instead of address of array 1. Later in the loop, the instruction LDR R3, content of R0, #4 expects R0 to contain the starting address of the array. To load the address instead of the data, replace it with LDR R0, equal to array 1. Run the program again. Now R0 contains the actual address of the array and the loop reads the intended data. The first issue is fixed. Now let's continue. The array contains 4 elements 20, 30, 40 and 50. So the loop should execute exactly 4 times. However, notice the counter initialization. Move R1, #5. The loop counter is initialized to 5 instead of 4. Let's step through the loop. The first iteration loads 20, the second loads 30, the third loads 40, the fourth loads 50. Everything looks correct so far, but the loop executes once more. During the fifth iteration, the processor reads the memory location immediately after the array. The value does not belong to our array. Whatever value happens to be stored there gets added to the sum. As a result, the final answer becomes incorrect because we are adding one extra value. The fix is simple. Change 5 to 4 here and the instruction becomes move R1, #4. Run the program again. The next problem appears immediately afterwards. The loop counter is decreased using subtract R1, R1, #1 followed by branch if not equal to loop. But the program never exits the loop. Let's understand why. The branch if not equal instruction checks the 0 flag. However, sub only performs subtraction. It does not update the condition flags. Since the 0 flag never changes, branch if not equal keeps checking the old flag value. As a result, the branch condition never becomes false and the program remains inside the loop forever. To update the flags after subtraction, use subtract with a set condition. Run the program again. Now after 4 iterations, the 0 flag becomes set. Branch if not equal becomes false. Hence, the loop is broken. Now, the program exits the loop and reaches this instruction store R2, result. At this point, R2 already contains the correct sum. So we expect result to contain the same value. In order to locate result, since we don't know its address yet, I'll temporarily load it into a register using LDR R4, equal to result. Now register R4 contains the address of result. I'll copy this address into the memory window to verify whether the value changes after the store instruction. As you can see here, there is no change in the location pointed by the label result. So now let's see why exactly it is not changing. Look at the declaration of result. Area, data section, data and read-only. This places result inside a read-only memory section. Read-only memory can be read, but it cannot be modified. So change it to area, data section, data and read-write. Build the program again. But now you will see a new error. The bigger problem this time is they have not even specified what exactly is the offending line. But one thing to note here is this error arised as soon as we changed read only to read write. So it means the instruction associated with it is causing some problem. The store or str instruction stores data to the memory address contained in a register. But here we never loaded the address of result into any register. Instead, we are directly using the label. The correct sequence is first load the address of the result, then store the contents of R2 into that address. Now build and run again. Open the memory window and if you check now, result contains the correct sum. The storage problem has been resolved. Let's continue. The next instruction is store R2, content of R7. Inspect register R7. Notice that nowhere in the program do we initialize R7. Its value is 0. That address belongs to the program's code section, which is read only. Since this instruction is not needed anywhere in the program, the simplest and correct solution is to remove it completely. The final instruction is now move R15, #100. Since R15 is the program counter, writing to it forces the processor to jump to another address. In this program, address 100 does not contain the next instruction that we want to execute. As a result, the processor leaves our program and enters an exception handler. In the debugger, you will notice the PC changes to an exception vector and the LR is also updated automatically. Since our intention is only to end the program, this instruction is unnecessary and should be removed or replaced with an infinite loop such as stop branch to stop. Now look at this declaration array DCB10. Search through the entire program. Notice that this label is never referenced. The program only uses array1. This variable serves no purpose. Unused variables consume memory and make programs harder to understand. So we simply remove it. Now build and run again. And finally obtain a fully working code that correctly computes the sum of the array and stores the result in memory.